So what I did last week is I went through a whole sort of rigmarole of different ways of drawing circles. Like, well, specifically the idea, hey, music links, how you doing? I'm good, thank you. Good to see you. So specifically, what I was doing was showing different ways of drawing, of making an object move around in a circle, and the idea was specifically to start with it at a certain distance from the origin and have it move around in a circle from that starting point. And so there was this, which used trigonometry, the tan2 function, to get the angle and then changing the angle over time. Then there was this simpler version, which was simply using the Unity API, which was a bit cheating really, in a way, because you don't really understand what it's doing, and that's not what we're about here. We're about understanding how we how things work, and specifically mathematics. I mean, it's about the grey cells as well as the grey beard. Yeah, basically the difference between just, I suppose, doing something, just focusing, you say you want something to rotate, and so you just ask the API to rotate it, and that's not really programming. Programming is where you understand what it means to rotate, and you're capable, if necessary, to rotate yourself, because there are some times when that's going to actually be needed. So in this case, yeah, you just wrote, okay, fine. Now, but then using Unity quaternions, you could do the same thing, which is what I did here. So this is using quaternions in order to rotate about a point. And then I went and said, but you could always use the old trick from way back and just do it like this. And so with 2 lines of code, you can cause a rotation. So currently, if this, let me see, I've got my sphere here. If I remove the whatever script and then attach the circle, can I have the circle here, please? So I have the circle script. Let's see what happens. Yeah, it is in fact right. So we're going to go and look at this from above. And set the height to 0, so it's actually in the thing. And so this is a circle, which is by itself, yeah. So what? Except that this is being drawn with 2 lines. This is my favourite circle drawing algorithm because you can implement it in assembler or assembly programming. You can implement it on the most primitive computer. If you really want to know how to make things move in a circle on the most retro platforms, all you needed to know are these 2 lines. Of course, you'll say, but wait, you're cheating. So, well, how so? How am I cheating? I'm cheating because I'm using floats. So if you were working on a very old computer, you wouldn't be able to use floats. Because they didn't have floats. It's like if you're working on your VIC-20 or your Commodore 64 or your Acorn Atom. You see, that's the weird thing, is I really didn't, back when I was doing the Acorn Atom, I didn't fully understand this algorithm. I think I do now, but it was in the Acorn Atom manual. That's how I got exposure to this algorithm. But the point is, you say, well, you know, if you've got floating, what if you? So I'm going to just do something here. I'm just going to recode this so that it's using fixed point mathematics, just to prove to you that even on the most primitive of computers, you could draw fast circles. And it's not just enough you draw a circle, but fast circles without using any trigonometry, without using angles, by using this algorithm. So the first thing that you want to do is, at the moment we're taking the position of this as being from transform position, which means it's floats. So, I mean, this is cheating. We're going to go really old school here and go int x and int y. Y will be z. Because I'm actually going to go backwards. As when you see what I'm doing here is I'm sort of recoding a simple problem in a more and more primitive way. But why? So that we learn stuff. And maybe, you know, people might learn a little bit of some of the things that I learned when I had to work in the primitive stuff, because the primitive stuff was all there is. And a very strong point that I like to make frequently is that you miss a hell of a lot out when you haven't forced or been forced to work with primitive, what seems like primitive hardware. In other words, when you overcome the limitations that you have of primitive hardware, you become a better programmer. And this is perhaps one of the problems that we have these days, is people don't train themselves to be better programmers because they're always just, you know, victims of convenience. So maybe, well, I wasn't directly in, this wasn't a plan, but I feel like it's a good idea. So we're going to go backwards so that I'm going to redo this circle in some form that would have been similar to how it would have been done in assembly programming. Well, I'm not going to get to assembly. So one of the rules that we had was that there wasn't such thing as floating point. Another one is that we didn't really have vectors. You could sort of make them. Why not? we didn't really. Sorry, is that a question or is that a statement? So yeah, we don't actually, you can't actually see the chat here. Maybe I can bring the chat in, like so. How's that? Then we can see the chat. I've got to take it away. It's not a serious question. There's no such thing as a serious question. There's only such thing as sincere questions. Yeah. Anyway, right. So I don't know why I felt that was funny, but I did. So I laughed. It's cluttering my screen. Now you can go back there. It's all right. Yeah. Okay. Keep changing my mind. So look, one of the things was there wasn't any such thing as vectors. In fact, and I mean, unless you were programming in assembly programming, I suppose you could create, even in BASIC, you could kind of make a vector use an array, right? But we're just going to use variables for a minute because we're going to go really old school. And also just to actually sort of understand what's what here, I think I'm going to create an old school region. Why don't I? Yeah, so here we go. Oh, I hate it when it does that. I just want this. Oh. Tries to be helpful. I can never turn that off. I like my editors to not be overly helpful. This is the retro section. So in here, because obviously I have to connect this to the rest of it, which is not retro, we're going to have an int x and an int y. Now, this is going to represent the position of the thing that is going to be spinning the ball. Yeah, I'm in 2. So, because the rule right now is I'm not going to use floating point, except where I have to tell Unity, because Unity wants to have floating point to work with, right? So, but that's in this section, no floating point. All right. So what I'm going to do then is create a function called step circle, and I'm going to just copy these two lines. These two lines that were the lines that I showed you, which were working in floating point. So you could just go, Z will become Y. So let's do this, and we can get rid of that, and so it becomes like that. Now, the first thing you're going to see there is a problem, because these are dealing with integers. So the distance from here, oh, hang on, if I grab hold of that ball, and we can see that, say, to the edge of this is about 5 units. So if I only have 5 units, I mean, that's a problem, right? Because the resolution that I have is very poor, and it's going to be 10 by 10 positions if we use integers. So I tell you what, let's go and use something that's a bit more like a resolution of retro computers, a resolution of 256 by 256. So what I'm going to do is create a function called move. Can't write now. Move, and it's going to take an int x and an int y, because we're doing this all in the very old school way, instead of taking a vector. And what it's going to do is move with, we'll say, a resolution of 256 by 256. And so we're going to give it a number between 0 and 256 for the x. That's like pixels on the screen, right? Do you understand that? It's pixels. I mean, when we worked way back on these machines, we didn't think in floating points. We thought literally in pixels. You've got to, if you had like 320 by 240 pixels, that's what you had to work with. And so that's what you would put for your number, to number the pixels. So it kind of makes sense, right? So this is going to be x and y in the range of 0 to 255, and gives me, you know, a plethora of pixels. Okay, that is actually, this is one of those things, right? This is sort of retro, but isn't. So this is actually now a little bit of lesson in architecture, because I feel as well, I mean, why don't we throw that into, I mean, you know, because it's all, I hit the wrong button. There. This is the retro section. This is the retro modern interface. And this is the modern section. So what the rule is that in the retro section, I'm only allowed to put retro things. So I'm not allowed to use floats, for example. In the retro modern interface, I am allowed both. It's going to take the retro coordinate system, integers, we want to go 56, but in order to be able to actually work, it's got to talk to the unity bit or the modern bit. So in this area, this is the interface area, you're going to have both. And this is a very common kind of way of splitting up an architecture as a cross-platform for development. You basically end up with 3 layers. You have the platform independent layer, you have the interface layer, and then you have the platform dependent layer. The interface layer is usually very thin. It doesn't do very much. It's just like a little bit of glue or translation. So you're going to see exactly that here. And in the modern section, we might, well, it's becoming like a little marketing. I'm going to keep some of this in here. For example, the begin rotation. This is a platform-specific problem of, you know, I want to wait a second before I start actually running my loop so that you can see it begin properly without a big hiccup, which is something I covered before. We're going to leave this the same. But you see, it doesn't matter because this is platform-dependent stuff, right? And so this is all throwaway, frankly. I mean, this is not the precious stuff. You don't port it to another platform, or you're going to port it to a newer version of Unity. You know, versions of Unity every 5 seconds. So it's like this is always in flux. You know, they can always deprecate something that you want to need. You might end up with Unity deprecating floats, for example. I mean, nobody knows. I mean, you have to trust that they're not going to deprecate floats or even obsolete them. It's a fairly good guess that they're not, but you can never be absolutely sure. But I'm being very tongue-in-cheek, obviously. But as such, this bit is actually the least important bit. I kind of going a little bit from maths into software architecture, but seriously, this is the least important part. I mean, even though it's actually the part that in the end makes things go, so to speak, the actual really important part is the why. I mean, the why we're doing this, and the why we're doing this is in this section. So this is a bit like your game. You know, your game is the most important part. The actual implementation on a particular platform, there, who cares? Unity, of course, does this for you because it is beg your pardon. It is an interface layer. Only it's a different kind of interface layer to this model, because in this model the interface layer is very, very thin. Unity is a huge, big behemoth of an interface layer. But anyway, I digress. I'm having fun digressing, I have to say. I should digress some more. We could look at this. I have to, in retro modern interface section, actually call Unity. So we can get rid of this, because that's part that belonged up there, right? In the update phase, I'm now in the world of platform specifics, right? I get the position. It's on the up. Oh, wait a minute. You know, we have an issue, because how does this get called? Oh, this is a classic problem. It's like, how does the main loop happen in your nice architecture? Well, there is a pattern I like to use, which I think works very well, and that's the platform calls the update function of the game. It's something that feels a little backwards, because you think the game will be driving everything, but in fact the realization comes eventually, no, that there is a game loop, and when the game loop is called is a platform specific thing. So what you do is you have the main loop of your game called by your platform, and so that I'm going to do that here, because this update function is what's called every frame. So I think we'll just get rid of this for a minute. So just clean it up. So in the update function, I need to call the game. So what I'm going to do is create a function here. Oh, you'll notice, by the way, I'm actually structuring all of this with 3 different layers: the game or application, the interface layer, and the platform layer, all in the same class. That's because you are allowed to do that. Hi FME, how you doing? Good to see you. Yeah, you are allowed to do that. I mean, I know these days programmers have hammered into them. You want to do something, you first of all conceptualize it as an object. Problem right there. You want to do something, so you that's a verb, right? And so immediately you have a verb, you need to create a noun. And this is that's already off topic. This is going on about my bashing of object-oriented programming. I'm not going to go there right now, as much as I would like to, because I seem to be in that kind of mood right now. What I'm going to do is just point out that you can absolutely structure your code well without using classes. It would be really silly for me to use different classes here, because you wouldn't be able to understand what the hell I'm talking about. It's like, this really small piece of code, right? But I'm still, smallest piece of code, I've got to structure it nicely for this one. Okay, so what I've got in the game section is I want to have a main loop. I know it's called update in Unity, but I can't call it update again because we're in the same class. But what I'll do is call it main loop instead. Except it's not a loop. It's not really a loop. Execute. I actually I'm fine, thank you. How are you? Traditionally, in my code from days gone by, I always called it exec. So here it is, exec. Execute a loop. So what you do is I call exec from here. So now every time Unity section here, this is Unity with the modern interface, retro section, game, So what I'm going to do is every game loop, it calls exec. So now, hey, my game just needs to, there it is. Beautiful. If you want an initialize, you can also do that. I mean, often we have an initialize function so that the platform would first call the initialize function of the game, so the game can initialize itself and then call the exec. But I'm not going to bother with an initialize here right now. Cool. Now, in order to actually move this thing, we can then say step circle move. And it should start to make sense, right? So it's like step circle and move. So this is now, if we just sort of, okay, going too far there. This bit here, just this bit here, right? That is actually my real code. It's very, very simple, as you can see. The rest of it is the interface and then Unity's stuff. How are we about there? Well, first thing is that I called it rotating, but what I call it is executing. As you'll see why in a minute, because naming things is very important. It's not just about rotation now. I'm creating a little mini engine in a class, right? So let's use a name that's a little more abstract. So, and then we go here, rotating is true. So then in here, well, executing is true. If executing, call exec. So I think that's good. Then as we look at this, it's still not quite working yet because we haven't finished our implementation of move. And that is where it gets interesting. So I'm going to say that move here has access to the transform. We're allowed to have Unity stuff in the interface layer. So transform.position equals new vector 3 x0y, because I have a coordinate transformation which the interface layer is taking care of. This is where the x becomes y, so that my screen coordinates have y like this and x like this. If I was really to go very retro, I would have y going down the screen so that 0 is at the top. 0 would be at the top. And as you go down, the y would increase. Lots of interesting reasons why traditionally the coordinate system in 2D space on screens went in reverse in the y, which I won't go into right now because we will never end then. Okay, well, the interface layer, copes with not just calling the APIs, we're interfacing between your game and the calling the API of the platform, but it will usually also handle things such as coordinate transformation. So that's what's happening here. I'm using Z instead of Y by Z. So we could do that, and then we're done. So let's check. So after 1 second, it starts executing, and it executes. It's going to execute step circle, which does the actual circle algorithm. Ta-da! And then does a move. So it will move the ball to the current point, and this should cause the thing to spin. Okay, are we ready? Let's try it. It's working perfectly. Very suspicious because it wasn't supposed to work at all, or very well. And of course the reason is, we have to debug this. So what you do is you go through the whole debugging process. You look at your code, and you go, why? And then you say, I don't understand. Things that I'm changing aren't really changing anything. Like I put this in, and I come back here, and I hit play, and I don't see the message. And eventually, after spending a whole day on this, or half a day, variations of this have cost me a day in the past. You suddenly realize that you're not actually compiling the file you're editing, or in this case, you haven't actually saved it. So let's try that again. All right. Debugging, that's what you have to do. Yeah, so as you can see, it's broken. It just seems to be stuck in the middle. The reason is because if we look at the coordinate system that we have, say of 256 by 256. Oh, well, you know, I'm not looking at where it's put in Unity scene here at the moment. There is a good reason why I'm not. Because I had this split. So for this section, the retro section, to know where I placed it in Unity means I'd need to create an interface going backwards in some way. Sorry, Dino, not being ignorant. Didn't see you streaming when you first started, but is this worked on games? I know this is a maths workshop, but it's turned into a little bit of an architecture thing as well. But so yeah, it's just a workshop. So yeah, I would need to have some kind of interface sort of communicating sort of from Unity up into my little retro section. So that is not going to happen, but that means that these are initialized at 0. But it is. I'm kind of giving coding for games. It is kind of a games programming workshop, but that's focused. These are effectively at 0, so the reason why that pops to 0 at the beginning is simply because, well, the ball's at 0, and then, you know, presumably it's not going to get to rotate. Because that's the other point, is to get it to rotate around. Well, 0. Coordinates. Yes. If the resolution is 256 by 256, and I put 0, 0, I should be in the bottom left of my square here, which I happen to know is 5 by 5. Right. So if, well, 5 plus or minus 5, if I take that ball, so it goes from minus 5 to plus 5, right, in each. 0, 0 is here, but that's not, if I want to be really, in fact, let's go the full retro, 0, 0 would be up here. So I need to apply that transformation in here. So how does that work? Well, we need to map a value of 0 to 255 to minus 5 to 5. I need a symbol for some minus. It's like two. Let's just use the word 2. Needs to map from to 5. So so I'm just, because I can use Unity, I'm going, well, should I do it? I'll do it by hand, because you could always do just like an inverse lerpy thing. I'm going to show you that because it's quite handy. If you want to do a mapping from one range. Hey, 2H Strike, how you doing? Desmos measures, absolutely. I'll show you how to do this using a pattern that I use a lot first, which is the inverse lerp. So what you do is you do math F, and we're going to lerp from minus 5 to 5. So you can do that as lerp, linear interpolation, and from a minus 5 to 5 for a range of t that goes from 0 to 1. Okay. So in here, then we do a math F dot inverse lerp from a range of 0 to 255 for the input value of x. So float this pattern is really nice. So what happens here is that the value of 0 to 255 gets converted to a value between 0 and 1, which is then converted to value between minus 5 and 5. And inverse lerp clamps. So it has the other benefit that it will never go out of range. Although, to be honest, I probably want it to go out of range, but that's another story. So you could do that, and I'll do it the other way as well. But for now, I'm going to do it this way. So this is like so. Now, what should happen when I run this is that if I move this away so you can see it. Oh, there's the sphere. And we hit play, and hopefully, oh, it's still in the middle. Oh yes, classic. I often make this mistake. I've done a mapping, but I forgot to change the variables here, so it's still using the old one. Other times I forget that. So there are some things like I still keep doing. All the time, that's one of them. Ah, and there it is, he's down there. But it's the wrong side because I also wanted to flip the Y. So I guess what I could do is just put a minus in here so that 1 minus. So it's reversing. 1 becomes 0, 0 becomes 1, and this will invert the thing, and it should pop up there, which it did. So now that's fine. In fact, before we get to the circle, let's try, because I seem to have gone to this nice retro kind of angle here. I'm going to get rid of that and just try some classic little things. Increment X and increment Y every frame. What we should see is that should now start moving diagonally. But that's moving in pixels. In effect, it moves nice and smoothly because it's moving at 60 pixels per second. And that's a whole other story I can go into, which I won't right now. So that's where you can, what we have. So there's a few things, because we're going to get to drawing the circle. But first of all, we have to solve the problem, because you go all the way back to that time. I remember in my chemistry class once, I'm sitting there and I'm pondering over this problem, and suddenly I had a brainwave, and I must have been about 16 or 17, 16, something like that, and I had a brainwave and solved the problem when I should have been paying attention to chemistry, apparently. And the problem was, I didn't know what it was called, but it was actually fixed point. Something I used to tell the students is, you don't know how easy you've got it. Somebody can stand here and tell you about fixed point. I had to invent the damn thing. No, I didn't invent fixed point for the world, for the universe, for the video game industry, no, I didn't invent fixed point for anybody except myself. I invented fixed point for myself, just like many other people out there invented fixed point for themselves. Something that you can't really grasp these days is how the information to solve these problems just wasn't there. So you would have to figure it out. And I remember in this chemistry class figuring it out, because I couldn't figure out how to make objects move in more than 8 directions. Which all sounds trivial now, but this was a big issue, and you got nobody telling you. And in fact, when you go back to all those retro games, all of the early video games on 8-bit platforms, they almost invariably only had 8 directions of movement, and almost invariably the diagonals moved faster. And there's reason for all of this. It's got to do with integers. Because here I have an example of a diagonal motion. And if I get rid of, say, this thing, so I'm only incrementing x, then I'll get, movements in the x direction. You get that? I don't know if you can see, but it's moving slower. When you move the diagonal, you move bigger, you move more, you move faster. Why? Because when I am incrementing the position by 1 in the x and the z, I'm moving diagonally. If you picture in your mind a right-angled triangle with sides of length 1, how long is the you think about it, if it was one, you would have an equilateral triangle. You wouldn't have a right angle to it. Right? You've got the right angle, that distance is actually the square root of 2, which is 1.414 approximately. So it's actually moving diagonally 40% faster than moving horizontally. And this kind of thing used to drive me nuts. I'm going, how do we do this? How do I make this ball using integers move in any direction? Ooh, that was tough. In the game, until you figure out the answer and then you slap your head on the forehead and say, it was so easy. Because I'll show you what I did in the game Letteroids, which was my first full assembler programming game. And it still kind of almost exists out there in the field. There's a story behind that. But it was basically you had to run around with a ship and collect letters to refuel in alphabetical order. That's basically the idea. And I really wanted the ship to be able to move in more than 8 directions. So this is what I did. I managed to invent sort of directions that were somewhere in between by doing this. If I go and say int, it's just different ways of doing it, but int, say xd, I don't know what to call it. We do that, and then we can do this. If xd, I'm going to go really retro, and 1, that means if bit 0, of dx is set, so is that not equals 0? I'm not writing in C right now, there we go. And then you would add 1 to x, which I might as well just do in there, just to annoy the hell out of people. So this is basically saying every time. Oh, thank you, good catch. So every time it executes the if statement, it's going to increment xd by 1. By the way, don't tell me that you shouldn't program like this. That's a good way to make me mad. Because I know you shouldn't program like this. That's not the point. The point is that you should be able to program like this, and then choose not to. So what you do is you do xd++ here, and this returns whatever the value of xd was before it was incremented, and it checks to see if the 0 bit is set or not. And if it is set, it increments x. So basically it says increment x every other time. And if we do that, then suddenly you can have a compiler error just for you. What have I done wrong? The compiler really doesn't like this. The AND operator cannot be applied to operands of type int and bool. That's curious. Didn't you create that ST game kickoff? Yes, wdood80. I did, indeed. The Amiga game as well, and a few other games too. But it came out on the ST first, yes. So I made the game Kickoff and Kickoff 2 and other things. So, in fact, I use this technique I'm showing you here in Kickoff in order to figure out the direction of, or a variant of, same principle, to figure out the direction that something was lying in without needing to actually use angles. But that's another story. Anyway, I have an error, and probably the error has to do with the order of, of execution, precedence of operators here. I want it to do this first, then this. I think that will probably get rid of the error. Yes. So now when I do that, oh, hit play. Look, I really got a kick out of that because suddenly it was like, I can now move in more than 8. Oh, yeah. Bang. Yeah. There we go. There we are. Oh yeah. Go chew on that. Yeah, it's very easy to get banned by me. I'm just like a ban hammer. I just, there it is. You got to do it. I mean, anything you get compiler error, you got to fix the error. You got a bug in your code, you got to fix the bug. You get a troll up here, you've got to hit the troll with the ban hammer. Anyway, I love the way though it was almost like he was afraid, wasn't it? Because he said, "No, Sensi rules. See ya." It's like oh, I gotta get out of here before he comes and he gets me. I'm so scared. Sorry, I can't. It was almost fun that. It's been a while since I had a troll on. So yeah, I was really quite happy with that. And then you go, oh, but what if I want to do other angles? And then suddenly it was, oh, okay, maybe we can get other angles by changing the frequency with which we move on the other side. So of course, that was a little harder in assembler programming to do sort of really robustly. Here we can use the mod operators. I'm going to do a little bit of a cheat. In 68,000 you'd have that be a bit slow. But he knew it's coming. We all knew it was coming. We all did. Yeah. I mean, so if I do that, for example, then it will be move one every 5. So I think we should have a shallower angle now. Oh, compiler errors. That's not like invalid expression. I have a stray parentheses. This. Oh, that was a spectacular fail. Oh, it's because I'm not implementing XD. Right, let's try that again. Oh, wait a minute. Okay, that was not equal 0, so that was actually doing 4 out of 5 times. But if I do it 1 out of 5 times, it would need to be equal 0. No, I can't. This is C#. If I just dump the not equal 0, I will get an error. But, yeah, in principle, you're right. If you look carefully there, you can see it's kind of juddering. Because that is actually working by pixels. See? But the thing is that it was still like, now I can make things move in different, by counting how many steps over. It's not very comfortable though, it's complicated. How can I just make an object move in any direction and any speed as well? Because I mean, unless you do a trick like that, it's either going at 0 speed, or you can go 2 pixels a frame, or 3 pixels a frame, or 10 pixels a frame. How do you go half a pixel per frame, a tenth of a pixel per frame, a hundredth of a pixel per frame? And then, as I said, it hit me. What you do is you pretend you have a higher resolution than you do. And that's exactly what I'm going to do here. Just so stupidly simple. Here we have a resolution of 256 by 256. But here, I'm just going to show you the principle. It's effectively a fixed point. Resolution of 256 times 256, which is 65536, or 2 bytes. Right, 256 is stored in 1 byte. 2 bytes can store a number up to 65536. Yeah. So if I pretend that there's that resolution, God, that's a high resolution. They haven't made monitors with that resolution yet. But that's the thing is, internally in Kickoff, it actually uses a resolution, use 16.16 fixed point. So the resolution is 4 billion by 4 billion. That's pretty high resolution. There you go. Internally kickoff resolution. Virtual resolution. It could be a marketing point for that. But anyway, yeah, it doesn't mean anything. So if I go and say that the resolution is now that instead of that, what happens? Well, the first thing is that, well, let's see what happens. When I increment these now, and then I put, yes. The point is, though, that I need to map from one to the other. Okay. This inverse lerp here that created a number between 255 to 65535. 65535. 655 65535. There we go. And so now I have a virtual resolution which is 256 times higher than before. It's still just 2 bytes. This is going to be fixed point of 8.8, which is 8 bits before the decimal point, 8 bits after the decimal point, which means that each pixel is now subdivided into 256 subpixels, if you will. You can think of it that way. So if I try this, what do I get? It looks like it's not moving, but in fact it is moving, just very slowly. You really have to zoom in to see it. It is moving very slowly, but you see now I've got slow movement. I can move at 0, I can move up to 1/256th of a pixel per frame. You can see how stupidly simple the answer was. So by the time I went onto the BBC Micro, I was using this technique and used it on Astro Tracker, which was a published game that was a clone of asteroids, if you will. And that had the kind of the physics movement in there on the BBC Micro 8-bit machine, and I used 8.8 fixed point with that. So I'm using 8.8 fixed point here, and well, it does mean if I want to move this at the speed that I had before, then I need to just be a little bit careful because my velocity is wrong. It's very low, isn't it? So I think what I quite like to do is actually create a velocity now. So I tell you what, let's call this V and W. So V is velocity in X, and int W is velocity in Y. And now I need initialization. I'll just initialize it here for now. And the velocity in X is going to be 1 times 256. If I wanted to move at 1 pixel per frame, and then this 256, so that V and W are now at that velocity, 256 times bigger than before. Of course, this gets a bit tedious with multiplied by 256, but if we really go retro, we can always just do this. Shift it 8 bits that way. So let's see how that works. I'm not using step circle at this point, so that's disappointing. Why? Because I may have set up the velocity, but I forgot to actually use it. See, it's a bit caught out. Put x plus equal v, y plus equal w. Wow. Of course, maybe we want some gravity now. So now I've set this up, you can see how easy it is. to do certain things, like let's say gravity. In fact, what I'm going to do is put the initial velocity in y to 0, so it should just move on in the x-axis now. Yes, it does. And now, going back about 2 or 3 weeks, we can go back to the whole thing I was showing you about how to implement gravity. Oh, well, the velocity in y, which is w, plus equal 1. Right, 1 is actually 1/256th of a pixel per frame. What happens? There's no bouncing at the moment because it gets stuck on the edge because it's clamped. Did you see that? We have gravity. It's one line of code for gravity, practically even in assembler. It's one line of code for gravity. There we go. Yeah. It's strangely pleasing. A little bit more gravity. We're going to do two-dimensional gravity in a minute in retro mode. So that's all good. What I'm going to do now is add a little bit of code for dealing with the boundary conditions. So I'm going to create an integer here, which is screen x is 256 rotated 8 bits that way. So this is the screen resolution in our fixed point representation. If x, and before I do this, I think what I'll do is just capture the previous position, px equals x, in py equal y. So we remember where the previous position was before we do this operation. If x is less than 0, I'm going to write these out explicitly because actually it's more likely to work first time. So we do, if x is less than 0, then v equal minus v. So I'm going to reverse the velocity in x if I go off the edge of the screen. And taking a tip from a few weeks ago about making nice stable bounces, if you remember, you do this and then you reset the position back to where it was before the collision. So I'm going to do that here as well. So x is equal previous x. Okay, so we're going to replicate this pattern 4 times, 2, 3, 4. If y is less than 0, reverse the y velocity and reset y to the previous y. If x is greater than or equal to sx, equal to, because if you have a screen resolution where it goes from 0 to 255, then 256 is actually off the screen, right? So we're going to, okay, so x is greater than sx, then what we need to do is reverse v, and then we set the x position back to where it was, which is the same code actually as we had up there. So actually, in that case, I might as well just do this. Or, well, and well, I'll just delete that and just make a Y version of this here. So this is how we used to do it. You write the same code out for the X and the Y all the time, and then worry about copy paste errors. Okay, so it should bounce now. Let's see. Ta-da! Hello? What's it playing? Hello? Are you going to start at some point? Oh, it's paused. Oh, there we go. Right. It's also, I also find this rather pleasing. It seems to move better that I'm using integers. Could this be just my imagination, or is it actually moving better because they are integers? That is interesting. I swear it feels different. Now, I don't know whether that's just my imagination, but there is actually some reasoning why, if you use fixed point, you might get movement which is perceived as being smoother. I won't go into that now. But there are some, I think the main point to bear in mind is that there's less of floating point noise. I still don't think I can really see it. Maybe it's just that this form of programming reminds me of when I was programming like 40 years ago, and so it's some kind of nostalgia thing going. I don't know. Anyway, yeah, that's working. And so what we have here is the integrating by adding velocity to position. Notice I'm not using any time step multiplication, so the assumption is that t, the time step, is 1. In this case, 1 frame. Because the units would be wrong. You need to multiply by time. But if time is 1, right, and it just simplifies things. You didn't worry about it. And if you're writing in assembly, you really don't want to multiply by delta time. Because that's just totally going to make things slow. Anyway, so in the code here, we add the velocity to the position, and we increase our y velocity by adding gravity. So this is gravity here. Okay, that's nice. I like that. So that's a fixed point bouncing ball. I'm wondering if is it gaining energy? I think it is, isn't it? To see. Yeah, I think it's definitely gaining energy. Which means that I need to do the gravity first. I need to increase the velocity first, and then oh, that just sort of touched, right? Oh, it just touched again. Yeah, this one's nice. This is actually a stable bounce. The same thing I was showing you, well, a few weeks ago. There, though, I was with fixed point, so this is proof that the principles I showed you there even work. No, it was floating point before. This is proof that the principles I showed you there work in fixed points as well, which is quite amazing. They're always not gaining or losing any energy. All right, so this is all great. How about we do something a little bit more interesting now in this kind of retro perspective? How about we make the ball orbit? I like to make it orbit a gravity well. There was a game, I can't remember what it was called, but I think it was a vector graphics game, and you had a star and 2 ships, and you played against somebody. With it, and these ships were orbiting a gravity well like asteroids. They would fire, and the shots would get affected by the gravity well. And I remember seeing this and going, "How is that done?" It's actually really, really, really stupidly easy to do, as I will show you, even in fixed point. So the first step to doing that is I'm going to recreate the rotation of the ball around a point. So I have that code still here. That step circle, right? Only what I'm going to do is, you see, I can divide. If it was divided by 16, what I could do is actually do this. Shift 4 bits to the left, right, sorry, shift 4 bits to the right, and you're effectively dividing by 16. So shifts in assembler are really fast. And that's why you do it this way. I'm going to do a step circle, so we'll see how this works. This thing I have here, I think I'm going to put into a function. Ah, come on, gravity y, I'll call this. So I can just take that code and put it in here, and then this is a refactoring. So when you refactor, make sure you haven't changed your functionality. Even silly little things like this, you can still apply the same processes. Yeah, that's good. That's still working. But now if I get rid of the gravity, I can replace it with something else. So what I'm going to do is execute step circle instead. Just curious what will happen if I do this. It doesn't seem to be doing anything. So why? Probably because it's going the wrong way around, which I think I can probably fix by doing that. And I can make it go the other way, I suspect. Let's see. No, it doesn't seem to want to move. Let's try putting the thing at a different starting position. Let's say, for example, it's 100. Coordinates 100, 100. Yeah, multiplying by 256 because I've got to use the bigger coordinate system. Why does it not like? Ooh. No, I saw it try. Oh, there it goes. It's because it's clamped to the edge, it will not allow me to move the object outside of the area. You can see that in fact it's actually drawing the circle around this point. I want to draw the circle around the center. So that's so what I'm going to do is create another variable in there, which I'm going to call Cx, that's the center point. It's going to be 128, or the screen x divided by 2. But since we are retro here, I'm just going to shift it 1 to the left, right. I always get my left and right confused. Good, screen x, screen y. So that's now the center of the screen. So center of the screen, I want to position the object at the center of the screen. So Cx and Cy. So the ball is now being put in the center of the screen. Cx, Cy. Let's see how this does it. How this goes. Whoa! Do you know? I think this might be one of those cases where I can actually tell it to compile and not to keep running when it recompiles the C# code. It almost never pays to do that. I always had in mind to sort of figure out, recompile and continue playing. I always had in mind to see if it was possible to design an architecture for a project in Unity so that you could actually modify code while it runs. Lots of problems with that. So what's wrong with this? Cannot reference non-static field. Hello. Oh, the C# doesn't like this. This is where it gets really annoying. It will not allow me to initialize a variable dependent on another variable unless they are static. I could make them static. I will make them static because that really is going retro. That means there's only one of these in the whole project. It's a problem if you want to have more than one ball, but for now. See if that helps. Probably won't. Oh, it did. Okay, cool. That didn't change anything. Why? Now let's turn off step circle. Oh, I know why. Let's turn off step circle for a minute and just see where it places the ball. So this is a test. Oh, I didn't save. Let's try again. Test circle there. Okay, that's in the middle, which is great. Now, it's not drawing the circle around the middle because it's rotating it. This algorithm causes a rotation around the origin. I wanted to rotate around not the origin, but the center of the screen. So, in order to do that, we can do a simple thing. We take the x and we want to know it relative to the center of the screen, so we subtract cx. I'm using the variables in place, which is very retro. You'd always do that when you were trying to save memory and CPU cycles. So there we go. I subtract the center, I do the rotation, and then afterwards I have to add the center back again. This should, in theory, now be a rotation, stepping the circle around any point, in this case, the center of the screen. And I've still got the thing in the center of the screen. So what I'm going to do is put it off to one side. So this is going to be, oh, I don't know, let's say 100 pixels. I have to sort of 8. There we go. So it's going to be 100 pixels to one side. Hopefully, what you should have now is a rotating circle. No, that's a failure. So, okay, I want to debug this. Oh, I already don't have the circle. Okay. The center of the screen plus 100 rotated by 8. Now I have to watch out, it could actually be order of operators here that was the problem. Yeah, that's better. So what happened there was that it was actually doing CX plus 100 and shifting the whole lot over. When I actually wanted to shift only this 100 over and add it to CX. Okay. Anyway, now it's there. And now if we turn on the step circle, because that's turned off at the moment, then big moment we should get here is, let's see, oh, no, hurrah! This is, we're well on our way now. So what I've got, basically with this bit of code here is making the object move in a circle. This is not an orbit, because the orbit is what I'm going to do next, which is probably one of my favorite small little simulations. So the thing is, we have all we need to do that. So I'm not using this gravity Y at the moment, so for this reason I'm just going to sort of push it down on the screen. The current code to do this in our game layer is just that. We've got a screen resolution, a velocity, X and Y, the center of the screen in X and Y, and the position of the object in X and Y. And a few lines of code, and boom, you've got yourself a very nicely rotating object in a way that could be implemented without floating point and in assembler really easily. So I'm using shifts everywhere. I'm using a divide. Right. Okay. Next thing is to do the simulation. Shoulder. The next thing to do is a simulation of this orbiting the center of the screen. And we have most of it already. I mean, I have a velocity for this guy. I'm not actually using the velocity in the circle drawing, by the way. All I'm doing is manipulating the coordinates of the point. I'm not even using velocity. But we do have velocity because we were using that in gravity simulations. That's all ready. Let's do it. So what am I going to do? I am going to figure out how that point is going to be accelerated towards the center of the screen. So I'm going to call this orbit, and we have to start with the position. Of course, now I'm in this retro mode, I have to do everything manually, which is really good for sharpening those old mathematics skills. Otherwise, rust as you get Unity to do everything for you. I mean, I'm not even using vectors, so I can't just sort of get the length of a vector. I'm going to have to calculate the length of a vector, normalize a vector. I guess I have to normalize it myself. And so that's what I'm going to do. So the first thing is to think about the physics, the actual real-world physics. The real-world physics is that the force acting upon an object which is orbiting is proportional to, and so by saying proportional to, I don't need to worry about too much about the details of the constants. I mean, it does depend on the mass of the two objects. I don't care. I don't know what the mass is of the thing in the center of the screen. I don't care. I don't care what the mass is of this object that's orbiting. Don't care, because it will all just be 1. Whatever the constants are, it's going to become 1, or something less than 1. It's just tunable, that you will tune until it works. You know, in this sort of very engineering way of exploring the maths. So I'm just going to say it's proportional to, but if you're really getting into the detail, it's equal to a universal gravitational constant multiplied by the first mass, multiplied by the second mass, and divided by the square of the distance between the masses. Or the force is proportional to 1 over the square of the distance. And that's really the only bit that we're that interested in right now, because I'm not trying to make I just want to get the effect of gravity on the screen right now. So to say the force is proportional to 1 over the square of the distance. Well, in that case, I need to know what the square of the distance is. Well, if we want to work out the square of the distance from the center of the screen, then by now, hopefully, you'll be able to visualize this as being a triangle, where the two sides in x and y is the offset of the ball from the center in x and y. If you square that offset in x and add it to the square of the offset in y, then what you get is the square of the hypotenuse, the long side of the triangle, which will be the distance between the 2 points. So when you do in Unity something like vector dot magnitude, all that has happened is it has taken the coordinates of your vector, x, y, and z, squared them, added them together, and taken the square root. That's it. So I'm going to do the same thing here. We're of course using integers because I'm using a fixed point. And we'll just do the square of the distance, because I told you it's the square. Then there's always the square root thing. That's a bit of a pain, the square root. But maybe we don't, we do need the square root. But let's start with the square of the distance, because that's what this is. Square, right. So I'll call this d squared, dsq. I always call it d2. I always used to call it d2. You know, d2 is the distance squared, right? That is going to equal x minus cx times x minus cx. I really hate writing out an expression twice. So I tell you what we're going to do. We're going to create something called dx, which is the difference in x. That's going to equal x minus cx. And then we can do the same here with dy. And that's y minus cy. Hurrah. And then d squared is simply going to equal x times x plus y times y, because there is no square function. Sometimes I wish there was, but anyway, there we go. Wow. And now we want to figure out the force. The force is equal some constant. What's that constant going to be? You know, let's worry about that in a minute. We need to do a divide. So at this point, if you're working in a platform, on a platform that doesn't have floating point, it starts to become a little trickier, because, you know, if you're in assembler and a platform that's not floating point, you probably don't have a square root function. There is this famous, oh, thank you, well caught. Thank you very much, music against it. Well, yeah. There's this famous thing about apparently why John Carmack is a genius, because of some inverse square root function you may have heard of. This mythical inverse square root function that was really, really fast. And everybody looks at it, and there's this big weird number in there. And everybody goes, what is this? And they all go, John Carmack is a genius. Actually, he didn't invent it. It came from some other guy. In fact, nobody knows for sure who originally came up with it. And the principle behind this is actually not that difficult. And the reason why the number is a weird number is it's just a number that is found to minimize the error of the algorithm. There's actually very little magic to it. But the reason why that was a big deal was because on early computing systems, square root was a very expensive calculation. So any optimization or approximation or anything that could be done with the square root to speed it up was always very welcome. So here I'm going to have to cheat, or I write my own square root function. It would be fun to write my own square root function. Do I have time to write my own square root function? Whoa. I'm going to cheat first, get it working, and then I'll write my own square root function. Because I used to have a square root function when I ran in assembler. So anyway, but I digress, because there's also the other problem, division. So if you're working on like a 6502, an 8-bit processor, division was slow. That's why we were always using shifts. So this one would have been a difficult problem to do in assembler, because you would need to also implement a floating point divide, or even a fixed point divide. Even a fixed point divide is yeah, I mean, I could do it, but probably not in the next half hour. So actually, technically that means I'm cheating the moment I do a divide here. Let's cheat. So what we need to do is 1 over d squared I need to get somehow. So what I'm going to do is 1 is actually 256 in my scale of things. And I'm just going to say that. So I guess you can do at least integer division. I don't need to do floating point. I can do integer division. So let's try it and see. Now we have to start thinking about precision with the maths. It gets a little trickier. So the float is 1 over. This is effectively 1 over r squared, because 1 is 256 volts. Okay. So then, having calculated the force, I now need to know the component of the force in the two axes, in the x and the y. And to work out the component of the force lying along those axes, it's like you know how long the hypotenuse is, and you want to work out what the other sides are. Well, you need to know the direction. The direction is actually the direction of the vector between the center of the screen and the ball. You can see dx and dy. But to make that a direction, I need to normalize it. So now we've got a problem. But to normalize it, I need a square root function. So I don't know if there's an integer square root function available in C#. I'm just curious, is there an integer? It just takes a double. I don't think there is an integer. I'm pretty sure there isn't an integer square root function. So what I'm going to do is, you know what? Let's stick to our pattern. I'm going to have to ask the platform for my square root for now, which means that I have a dependency on my platform, but that's okay. I can actually do it through the interface layer. So this returns an integer, square root of an integer, x, is going to return an integer cast of a mathf squirt, internally by the way, the mathf squirt, square root, calls the math square root, which is a double. So that's the funny thing, is everywhere everybody's calling the square root function in Unity, under the hood it's calling the double version. So there's there's a conversion from the float to a double passed into the square root function, which calculates the square root, returning a double that's cast back to a float. It makes you wonder why they didn't implement their own square root function. There may be reasons. It might be that it would have been... No, I don't know. I think they could have done it natively. They could have implemented a native square root function that didn't use doubles. I don't know why. I mean, I would assume that would be an easy win, but I'm not familiar with all the design criteria of that and the consequences. But strikes me as anyway. Here, I'm having to convert the integer to a float that internally will be converted to a double, for which the square root will be calculated. Then it's going to be converted back into a float by the mathf function, which is then going to get converted back into an int. There's a story behind this with the whole of the normalize function that I go on about from time to time. Because that normalized function that in Unity that has a check to see if the vector is shorter than about 1/1,000,000th of the unit, which is too big for certain applications. What do you mean it's too big for certain applications? Well, like the size of a millimeter. You want to calculate the length of the vector or normalize a vector of 1 millimeter in length, you're going to end up multiplying 1 millimeter by millimeter because you have to square. You have to square it, don't you? Guess what you get when you multiply millimeter by millimeter? Yes. You get a 1/1,000,000th, and that can cause a problem. Anyway, so what we've got to do here is the int for the float mathf of the x. So basically this should do it. Don't think about the casting that's going on there. So now I have in my interface layer, I have provided the functionality of a square root so I can get past this problem. The square root, though, has an issue. Have you spotted it? Yes. It needs to be in the right units. So what I in fact have to do, I need to think about this, because if I put a 256 in there, that means 1. So in fact, I have to take this x after it's converted into a float, not before, because then I'm dividing an integer. I need to divide it by 256. I can't really use shifting here because now I'll be shifting a float, and that really doesn't make sense. But I have to do float x divided by 256. This returns a float, which I then have to multiply by 256. So I have to apply scaling in there. I'll take the x, make it a float, divide it by 256. So 256 becomes 1. I take the square root of it, but I get back 1, and then I multiply it by 256, and I get 256 back out. I think that should work now. Ooh. I'm making this a lot more difficult than it would be by trying to stick to this kind of retro paradigm, but you know, you learn more that way. So if I'm going to do that, it means the next step is to figure out the square root, because I need to normalize my vector dx. So how do you normalize a vector? You divide the vector by its length. So this becomes, I'm going to call this nx. Nx is equal dx divided by the length of the vector. I haven't got the length of the vector yet. The length of the vector is going to be d, and distance is equal, square root of the distance squared. Then I've got my force, which is 1 divided by the square of distance. Then I'm normalizing the x coordinate, which is the x divided by the distance. Am I allowed to do this? See, the problem now is that, again, that division, we need to be careful about how fixed point works with division. You need to remember this now. You see, if d was 256, it would actually be 1, which actually means that dx would not change. If 2, we want to divide it by 2. So I believe the correct way of dealing with this is 200, no. Oh, I need to multiply dx by 256 first. Let's try with some values in my head, right? We're going to say if dx is 100 and d is 256, I needed to stay at 100. So I believe I need to say 256 multiplied by dx, or we can do this, multiplied by 8, shifting it 8 bits that way. So if d is 128, then I multiply by 256, I divide by 128. I think that works. We shall see. Then the next is y dy. So if that's correct, then what we have now is the normalized x and normalized y of the vector between the two, which means that I can use that to apply an acceleration which is proportional to the force. The bigger the force, the more the acceleration. So I think that's what I try to do now. Now, velocity in x is v. I need to add to it a certain amount of this force. Multiplied by nx. So in effect, it's f times nx. I'm beginning to regret trying to do this in floating point now. There we go. Except, well, we need to watch out, because we can't just do a multiply of two fixed point numbers like this. Because if they were both 256, the answer should be 256. So I'm just think that what we have to do here is divide the result by 256 and just to see if this works. We have 256 times 256 divided by 256. Hey, Grumpy Game Dev. Yes, I am doing fixed point. What I'm doing is I'm showing how you can do a simulation of gravity in fixed point. I just, on a whim, tried to do it in fixed point. It wasn't my original intention, but I sort of like, I went crazy and said, let's demo it in fixed point. So I have to divide, 256 times 256 divided by, I think it's enough for me to do shift 8 this way of the result. I have to watch operator precedence again, although I think multiply would be before shift anyway, but just to be sure, I think that does it. Now, this means that the gravitational constant is somewhere in here. I'm going to call this capital G. Oh, there is this divide. G, that's also a square. Okay. So what I'm going to do is make G equal, say, 1, which is 1 shifted by 8 bits this way. Then I need to watch this divide as well. And I need to watch this multiply. And this is the lesson. This was the nightmare. What was difficult about doing fixed point was that you'd always forget to do the correct operation with the correct units. As I've actually seen, there's a bug there, because I can't just square these two, they're fixed point. So I need to offset them. So one of the ways you deal with this is that you could use macros, if you're programming in C, to allow you to do the multiplications. In C#, it's tricky, because the problem is the compiler is quite happy with them being integers. It doesn't understand there's two kinds of integers, which then I get onto my hobby horse about how, computer science with this crazy obsession, there are some good reasons why, but it is an obsession. Just because there are good reasons for it doesn't mean it's not an obsession. And there's an obsession with type safety, but it only goes so far. As if you were really serious about type safety, you would have the kind of type safety that would actually be useful. And one of the most basic pieces of type safety that would be useful is having conformance with units, because an integer doesn't mean anything. It could be, it's like, if you have a float, the float could mean meters or could mean seconds. It makes no sense to add meters to seconds. The compiler will just let you do it. So if you really were serious, if academia was really serious about type safety, they would have given us that form of type safety, which is the simplest saying. You can have units. So you can tag a variable and say this is in these units, and the compiler would tell you if you tried to do something stupid. I think there are some languages that do that. I'm not sure which, but the mainstream languages that we have, they don't have that. And you know why? Because it's mathematics. It's rant over. So unfortunately, F#, yay! Why? Why F#? Because F# is a functional programming language, so it's of only interest, apparently, to mathematicians. I despair of the world. Not sometimes, but pretty much all the time. So what I need to do here, if I do this square, I do need to afterwards shift it down by 8 pixels, 8 pixels, 8 bits. I can add and then processing. You're right. You would end up with better precision that way. Yeah, good tip. I agree with you. I was playing it safe, but you're quite right. I should be able to do that and then do the shift afterwards. You could other wind up off by 1. Oh, yeah. You could by 1 term. Yeah, you're correct. There could be a small error there. It's true. It would be more precise. I mean, basically, the rule is that you put the division right at the end. And so what I was doing wrong, what caused the lack of precision is I would have be dividing these two down before doing the division. Rule of thumb, put divisions last. That is correct. Also, that was from habit. Um, the disadvantage of doing this is that you run into a greater danger of hitting the upper limit. But I'm kind of doing cheating fixed point here, where there is no upper limit. Um, well, in practice there is, but it's very big. Yeah. Hi there, Sultan. How you doing? Yeah, and then you can pass back. This is all true. You can do that if you're writing in assembler, then that's going to cost. So it's always a balance. In fact, you would end up sometimes really analysing an expression and seeing the possible input values and the ranges that you can get, and making sure there won't be an overflow or an underflow condition. It's could be quite tough. Fortunately, we rarely have to do this these days. But the point is the fact that one can do it makes one a better programmer. So again, it's that thing that I believe that you should know and be able to do all kinds of horrible hacks and then have the discipline not to do them. But you're a better programmer if you know how to do them, because it informs the way you think and reason about programming. Right? It's a bit like if you're a musician, you might be able to do some crazy practice scale or crazy practice routine that's absolutely, just showing off, and just not musical at all. But what it's doing is it's developing your technique. And you wouldn't play that to an audience, right? But it doesn't mean that you shouldn't do it or shouldn't be able to do it. And this idea, which is very, very reasonable and easy to understand in other contexts, I have no idea why it is that when we get to something like programming, is you've got people shouting at you all the time. You don't even think about using an exclusive OR. If I saw you use an exclusive OR, I would fire you on the spot. I think I say that practically every stream at some point. It's like, no! You absolutely should know how to use an exclusive OR for a hack. Absolutely you should know. And you should also know not to use it. That was it. Yeah. Well, I think that, Grumpy, I think it actually does help people who mostly make a rounded rectangle the correct shade of blue. It even helps them, because it will help them understand when they should stop making rounded rectangles with the correct shade of blue. It's just the same problem, same thing. Keep hitting the microphone. Anyway, right. So back off that. So I think I fixed that one, and then I've got that, and then there's this divide here. So when you do a divide one to the other, I actually need to multiply this first. Now, you see, I could multiply the whole result, but that's wrong. The rule is put the divides at the end. So to maintain accuracy, so we do that. Of course, as Grumpy Dev was just pointing out, this does mean that there's a potential for an overrange. But I'm not covering the whole thing about fixed point and how to do fixed point and dying art. I could go into that, but it's really not that interesting. But mathematically, well, it is actually, but mathematically, this is as far as we need to go right now. I'm not going to worry about running out of bits. Just use boost, exactly. Yeah, just use boost. So I think we're fine. The square root function is already adjusting the thing. I think for this reason, I need to change the name just for help clarity. Squirt fixed. So that we're all clear. And then, so what I do then is I add a force, and believe it or not, that should be it. That should be done. We should be able to have the thing orbiting the center now. So of course it's probably not going to work. And there are a few other little things that need to worry about, like we need an initial velocity. Oh, I do have an initial velocity. We need initial position. What is the initial position? Let's remove. I'm going to turn off the step circle in a minute. Oh, yes, I turned that off, didn't I? I said let's see if I can actually edit. It worked. Well, of course I don't know where it's starting, so I'll have to restart it anyway. Oh, it does start there. Okay, and what I'm going to do is I'm also going to create an integrate function. This is just going to add acceleration to velocity v plus equal oh, I already did that one. So what I actually need to do is x plus equal b, and when adding or subtracting in fixed point, you actually do not need to do anything, that just works. We put those who don't think, those who do think, and those who overthink. Most don't think, most don't and don't want to. But I will add to it that the most dangerous are the ones who don't want to think, and so don't think, but want to tell everybody else that they shouldn't think as well. And those are the ones that I find, and there's a lot of them about. They're the ones that they practically rule Stack Overflow. Here's a perfectly reasonable question. Stack Overflow, perfectly reasonable question. The number of times I've been looking for an answer to a question, and I find the question that I was looking an answer to actually asked. And I read the question, I go, that's perfectly clear. Why was it closed? And it was closed because somebody came along who didn't understand the question. And so when they don't understand the question, they assume it's because there's something wrong with the question. Manly. I agree with you, Grumpy. Programmers care about what goes on under the hood. Developers just use Boost. Just use Boost. It does exactly what it says on the tin. A little bit of Boost. You want to boost your career? Use Boost. I think it's not a coincidence that Boost begins with a B and ends with a T. Just like the word bloat. Anyway, so what I want to do is the integration. So the integration here is adding the velocity to position. Again, with the caveat that the time unit is 1. Bullshit. Yes, you have a point. Well, that's crazy. If you're learning to code, don't learn. Oh, man. Oh, you got me going. Oh, that's terrible. You don't learn anything. You don't learn anything at all by learning an API. That's not learning how to program. This, what I'm showing you here, is learning. This is real programming. That's my point, in a way, or one of my points, is that when you actually go down to the bare bones of it, that's really good training ground for your programming skills. Because even though I don't use fixed point anymore, I use the muscles that I developed in the time that I was forced to use fixed point. They made me a better programmer. There's no way around that. But it's like somebody's trying really hard to sort of build up the running capability physically, and they're running around the track. Hey, I'm running, and you was, Heather's running. I'm really working very hard to get myself into physical fitness so I can run as fast as possible. And you have the crowd shouting at you and going, why don't you use a bike? Hey, useless pony! Wow, it's been a while. How you doing? Good to see you. Sum up the positive values in an array. Return R filter X to X greater than 0, reduce A to the A equal P. It doesn't teach the newbie anything. It doesn't even teach me anything. I'll be honest with you, I'm looking at that arc filter, everything. I'd have to sit there and really work that out. And it's going, so that is sum up the positive values in an array. Oh my God. Okay, so you're filtering out the values in the array, looking for only the values which are greater than 0. Then you reduce A, B to A plus B. I can only assume that the reduce, I don't know, I'd have to look up what the reduce API does. I don't know, I'll use reduce. I'm going to guess it kind of does a recursive summy thing, or sums pairs, applied to pairs. Does it take, I don't know. Does reduce take an element of the array and then take all the elements of all the remaining elements of the array and then apply a sum A plus B, and this ends up with a recursive sum of the whole lot, which was just this like, whatever! It's just, what that is showing off. You know, unless there's a reason. Unless there's a damn good reason for it to be done that way. You know, I think there are clearer ways to do the same thing, but maybe I'm wrong. Fold operation, okay, yeah, so it's taking, I gotcha. So it takes A, it says add to A all the other elements, and it just keeps on doing that until in the end you get. The thing I've found is that whenever you do clever things like that, you almost invariably end up undoing them later, because there's some reason why it wasn't suitable. Yeah, I agree with you. That's absolutely right. I'm totally with you on that. I mean, but we would take, if in order to think functionally, it's perfectly good, and that is just like a variation on exactly what I'm saying. If you're taking it from that perspective, but my reaction was from the point of view of somebody learning how to program, like not functionally. You know, and it's sort of like, wow, I don't know. Anyway, we should try this out, because I think, yeah, that's exactly right. And in fact, that way of thinking, I tried to help students with that way of thinking by teaching SQL, because my argument was that SQL helps you on that road. It certainly helped me on that road. But the problem was that the students had already had exposure to SQL in some course or other that they had done, where of course that whole emphasis of understanding a more functional way of dealing with things was completely missed. And so you get stupid things like students would be reading the entire array into the game, app, web page, whatever it was. They'd read the entire database in, and then do searches and operations on the database. So they were treating the database as just a way of retrieving raw data, which is just insane, because that isn't what the point of SQL is. And it was like, to get you to think functionally, it's like, oh, I need to sort of have a loop that goes from 1 to 100. And so you have to think, well, if you're going to use that in a kind of a functional way, you need to define the range of 1 to 100. And how do you define that range? And if you're really used to imperative thinking, it's quite difficult to switch that gear. It is not the easy thing to switch. When I started getting into SQL about 20 years ago, that's when I started more. About 22 maybe. That's opened my eyes to this other way of working. I mean, they're not saying SQL is technically a functional programming language, but it has some philosophy that points you that way, right? Where you are specifying what you want done and you don't say how to do it, and then you trust the thing will do it. So you're doing a join between two big tables, and when you're used to imperative programming, you're getting terrified because you're saying, but it's going to sort of do every row of this table against every row of this table. Oh, that's going to be impossible. That's going to be so expensive. How can you just do? No, you have the temptation of trying to sort of optimize it because you can't help yourself. And in fact, the point is the whole system optimizes itself. That's the whole point of it. You tell it what you want, and it's up to it to figure out how to do it efficiently. It takes quite a lot. It took me quite a bit to get over that. It was not easy, but yeah. Sorry, I've gone off here. There's a really interesting discussion. Oh, I've been fine, useless, Pony. It's just I had real life, Cursors. They taught them cursors. Curse it. I know what you mean. Might as well use a file, absolutely. Yeah, declarative, which is a middle ground. Yeah, okay, thanks, Grumpy Dev. Time for me to finish my thing. It's been waiting here on the edge of maybe working. I'm going to try it. Let's see. What's going to happen? Who knows? Nothing happened. Well, that's disappointing. And there's a reason why nothing happened, just because I'm not executing any code. So let's execute the orbit, and let's then also integrate. Oh, something happened. All right. So what I'm going to do is turn off the orbit, and then we can just see how this is behaving. And I want to change the initial velocity then. Let's put it moving in the Y. Okay, so that's moving there, but we're getting no gravity yet. I'm going to turn gravity on, right? And now comes the fun bit where we have to try and figure out why it doesn't work. Okay, now, one assumption, I could print values out, I guess, but let's try it without that just for a minute. One assumption is gravity is too small. So I'm going to just go up by a factor of 100 and see if that changes anything. Ooh, it did. Next problem. I suspect that my gravitational attraction is going the wrong way. So I'm going to switch the polarity of the force. It's actually pushing it away. I have negative gravity, I suspect, because it should be attracted towards the center. Oh, did you see that was a curve? And I'm going to up the gravitational pull even more. Oh, this is so exciting. Come on. You can do it. That looked very promising. Now, I'm going to run that again. Okay. So what we need to do is reduce gravity. And so now I'm doing tuning phase. I basically will split the difference. So we were at 1,000 was too much. Let's try. Ha! I present to you an orbit in fixed point. You know the amazing thing? It worked first time. The only thing I was missing was the the only thing I was missing was the getting the strength of gravity right. But in fact, the code is correct. Kind of behaving a little weird when it hits the edge, as you can see. I don't have the bounce code active. I'm going to turn that back on. So if after integration, I can put in the bounce. If I hadn't been doing all that ranting, I'd have been finished by 11 o'clock. So we know who to blame for that. Me. So come on. Now, in real orbits, it wouldn't have a precession about it. You notice how it's going around and it's sort of, it's now the thing is pointing downwards. It's also getting closer to the center until eventually it goes. This is all because it's an approximation. You know, because of the time step. I think what I'm going to do is change the time step. But in fact, actually, if you change the time step, it's really no different to changing gravitational pull at this point. So I'm going to just change the gravity constant, and it does look like there's a very large amount of precession, large amount of instability. But then do bear in mind, I am doing this in fixed point, and it's only 8.8 fixed point. So the precision is not going to be great, and there's not really a lot that can be done about that. I'm going to try reducing the speed a little more, the gravity a little more. That's too much and it hits the edge. What I could possibly do is bring the position of the object a little closer, not halfway, bring it in towards the center. That's not bad for 8.8 precision. If I wanted to get a greater precision, I would need to change how many decimal places I have after the point. PRC, I'll call it, which was 8. I'm going to look at all instances on, as a shift. PRC, so this is the number of bits after the decimal point. Currently only 8, but if I go through and look at all the cases where I have this 8, becomes. Why did I do that? Yeah, I've got to get the right. So this 2.5, can you put brackets around the 256 first here? The 256 is one shifted 8 bits. I'll now shift it by precision. So now what I can do is change the precision after the decimal point. We see if I have any other occurrences of 8 in the file. I don't actually. So let's just, that was a refactor, so I'm going to test to make sure that it behaves the same as it did before. Doesn't mean otherwise. Debugging is going to be a nightmare. What I'm going to do is increase the precision. So if I go to 16.16, which kind of precision that you would have on 68,000, the 68,000 had 32-bit registers. So you could do 32-bit maths on it really easily, even to memory locations. Even though it's a 16-bit bus, it would do 32-bit operations, which is really nice. And you could do the fixed point part by simply using a long, that's 32-bit memory for your number, and just read it back as a word, and it would automatically read back the high 16 bits of it. So the conversion from, this beautiful trick, the conversion from fixed point to the actual integer would be just a read, as you just read half of the half of the number, and that's it, you have it. Let's try this at 16 and see what we get. It's not that much better, is it? In fact, it seemed to behave exactly the same. You know why? Damn save didn't happen there. Should we try this again? Oh, attempt to divide by 0. That's not good. How will it be entirely low? That's a sign that there could be a problem. But this is where it get really fun to try and figure out why. Why divide by 0? So divide by 0 would happen if the thing hit the center, in theory. Right, so this is 8 bits after the decimal point. Okay, so try and make a small change. Let's go 9 after the decimal point. Did I have 200? Oh. Yeah, the 256 here. That's the screen size. No, that's fine. All right, let's try 9 bits after the decimal point and see what happens. Oh, it doesn't like that at all. So I've got a problem. I broke something. I must have a dependency somewhere. Oh, it's here. Right, yes. So there we did the lerp up to 65535, which is 255 shifted left by precision. Even that's not quite right. Let's just go 256 shifted by precision. Screen precision is going to stay the same, but the internal precision is now 512 subpixels. Okay. Oh look, it's a little bit more stable, I think. If there are no precision errors, it will be completely stable. Crazy. Okay, cool. So let's try taking this up to 10. I'm going to take this to 11 in a minute. Oh, at 10 with failure. Now that's very interesting. So that suggests that there may be an overrange somewhere. So this gets fun, you see, to figure out what happened. If I multiply it by 10, some value has gone. The cheaty way of doing this is to just make everything long. Hello, R.W. Grimm. I've been raided with a party of 54 people. Wow. Have you seen that series on Netflix, Kingdom? We just watched tonight the end of season 2. That's crazy. All those hordes of zombies. It's like those. So immediately I was just reminded of that. It was raiding party of 54 people. So that's kind of interesting. But when I change the precision to 10 bits, you may or may not be the reason for the raid. Okay. Growth harvest. It's actually I enjoy the series. It's pretty good storytelling, I think, and it's actually pretty gruesome on a certain level, but it never really is that gruesome because it's so over the top. It just, yeah. I think you just got to you get used to it, I suppose. I don't know why. So normally when this happens, I know why. It's got to do probably with G. So this is showing you. So this is all the pain that you get when you do fixed point, like the old days, is overrange probably in this G, because I have 100 related to it. There's 100 that's shifted by 9, which is 512. So this becomes 100 times 512. So that becomes 512 or 51,200. But that is in this multiplication here. Oh, right. It's multiplied again because I have to multiply it up because I'm then dividing. So that gets multiplied by another 512. I need to get a calculator out. So this is, what we were talking about, number range. It's sort of like when you have a limited number of bits, you use fixed point. It can be, this kind of calculation can be tricky because we end up with 512 times 100. Let me just restore this back to where it was. But then in this calculation here is then multiplied by 512 again. And this is huge. This is 26 million. That's a pretty big number. That's then divided by this distance. But then I have to multiply it by nx again. And you can see here, so what you would do in practice to get around this problem is that all this is all broken down like this. It doesn't work because I'm getting a number over range. So what you do is you would collapse this down into a single expression that would be constructed in such a way as to make sure you didn't get an overrange in the middle. Oh, I haven't worked on that for quite a while. I was working up on it until I stopped. Maybe was it 6 months ago, and a bit more, until I stopped streaming. So that is being shelved for now, but I learned a lot from it. It was fun. So there isn't. Yeah, I was making a video game engine as an experiment, entirely from scratch, using. I mean, I say entirely from scratch. I was using something for the window integration, and I was using OpenGL. But I mean, as much scratch as was practical. Basically using OpenGL, and so all the shader stuff and the sort of scene graphy stuff, and I made a game out of it. That was like a Battle Zone type game, and you could play the Battle Zone game. And I was about to start doing network code, and I kind of ran out of steam at that point. I wanted to focus on my music more. So there we are. But all of the assets were all in the database. So I basically, with that project, what I wanted to do is to test out a number of theories about architecture in the video game engine. Yeah, I mean, it was literally the only thing that wasn't from scratch was that I wanted support for regular expressions, so I used the PCRE library. And there were some things I used Boost for. No, I'm joking. I didn't use Boost. I used to interface to the SQL library. I used the library that works with Postgres. I can't for GL. I don't know, some wrapper that allowed you easily to use OpenGL or get access to OpenGL. I can't remember which one, GLFW or something like that. But basically just to open up a window. But then everything else was written in C. And everything was written in C. And so what I wanted to test out were things like the theory that you could in fact store everything in an SQL database. Because one of the things that really annoys me about Unity is how it really needs a database. If I was involved in the architecture of Unity, I would be saying to them, you really need to replace all your zillions of meta files and all of this stuff that you have to keep track of the project. It's a mess. Use a database, because that's what they're designed for. But you see this very often. It's not just Unity, it's most game engines. You end up with initialization files. It's like, come on, this is 2020. Let's not have initialization files. Let's not distribute the state of our project amongst 300,000 files, any of which could go out of sync. Stop rolling your own search functionality so you can find things in the project. It's like, use a database. It's a solved problem. Database. But the problem is that it's that thing we were talking about SQL earlier. It's like programmers who are used to procedural programming often don't understand what a database actually is and why it's actually really good to sit there and develop a fracking good query. So these days I like it. I'm doing a radio station, Radio Radion. You know, Radio Radion. And Radio Radion, I'm going to build up scheduled programming on it and so on. Right now it's sitting there playing from, you know, random sample playlists, but I can schedule a show. We ran a show, the first show on Friday. I set it up the night before. I said 7 p.m. you play this. So what happens is it sits there and picks out tunes at random, and then as it approaches the time, it checks about the time available to the next show, and then it finds a tune that fits into the length of time available and plays that. And if there's a gap, it fills it in with jingles. And then on the time when the thing is supposed to start, when whatever's currently playing is finished, which is going to be short because it's jingles, if the worst case scenario, it starts playing the show. When the show's finished, it goes back to doing this really quite whole damn thing is written in SQL. Really, I enjoy it. It's really good fun. It's like write a query that tells me all of the tunes that have not been played in the last 2 hours, right, that fit into the remaining 3 minutes and 50 seconds before the show starts. Boom. And because in PostgreSQL, but I think also other things like MySQL, because they have views, which wasn't always the case in MySQL, which was the most popular of the database systems, and thus was responsible for people missing the point, is that if you've got views, you can create an architecture within your database so that you can create a view. This is how I construct complex queries, and what I did in Nugget, you know, with the C engine, is create a view that says things like, you know, this is the time of the next show. So there's a query to do that. Query itself is not very difficult. You make it into a view, and then you can use that view inside views. It's beautiful. So it's quite possible to create really complex queries and then as layers of other views, and then you put it in a view. And so then I have a view which is give me a song. Beautiful. Thank you very much, Music Link. How insensitive that was with my band, Dini Blanford Davis, some 15 years ago. And that was on Dini Blanford Davis. There is an album of Dini Blanford Davis, and I'm going to get that remixed and release it again. The superb, he was a really good saxophone player. He only played with us a little bit, and it was towards the end of Dini Blanford Davis, because I had to get work, and I had to move away. In fact, I moved to the Netherlands, so I had Dini Blanford Davis, and so I moved out and I started learning to live in the Netherlands. And that was the end of Dini Blanford Davis. But yeah, it's really good. Dave Perry is his name. I'm trying to get back in touch with him. No, Filcher. I'm in Bristol now. Locked in, like everybody else. So that's one reason I started a radio station. I kind of wanted to do something with music. I'm trying to, and it's also I've gone through the archives and found for the radio station lots of old recordings of Dini Blanford Davis, and I'm getting them. Simon, who's my producer, sounds grand, but basically I pay him to do some. I go to a studio which is nearby, and we've been doing that for 2 years to get the album out. And it was really close. And then we got this lockdown, so you know, so on. But I'm still trying to get these things done. Anyway, to get back to the topic in hand, precision. So I think I'm going out of range, which is fine. So the last thing I'm going to try here is the age-old simple thing of cheating. So let's use longs instead of. I don't know if it's a long. Actually, I need to check. Is there any difference between a long and an int? C#, long, and int. Yeah. Okay. It is a long. And so we can just go through, and as soon as I change it to a long, I've got 64 bits to play with, and it should be very difficult to get an overrange. When you're using floating point, the whole point of floating point is that it kind of adjusts the position, the number of bits after the decimal point automatically to try and ensure that you don't have precision issues. But as soon as you're using as soon as you're making your own fixed point, you have the responsibility of dealing with that. So let's see if I've changed all these to longs, and then it doesn't like something. I've got some errors. It doesn't like, fuck you, fuck you. I mean, geez. There we are. This problem again of type safety. So this is obsession with type safety. Won't let me just define 256. I have to actually tell it that I meant long. What? Okay, that can't be a long. It needs to be an integer. Is that the issue? But having given that, it will not allow me to ensure that I have units. What does it look like now? Cannot implicitly convert long to int. Where? Oh. There, I missed one. Okay, here we go. Are we there now? Oh, we are. So let's see if this runs. It's running. It's behaving the same. That won't have actually changed anything on using 9 bits. But I should be able to go to 16 bits now without an overrange. And as you can see, it is a lot more stable. There's still a precession. I think you can see it's processing a little bit. Not much though. So that was, as I thought, that was just down to, that seems pretty stable. We could probably go to 24 bits. I might be able to go to 32 bits. Well, I should be able to go to 32 bits actually. Let's go all the way. And make full use of the, well, it's not full use, that's the point. To make full use, you use floating point. Here we go. No, you can't use 32 bits. I get to divide by 0. Isn't that interesting? 24 bits, even with double, even with longs. And this, ladies and gentlemen, is why we have fixed point. Even that, 24 bits doesn't work. And the reason is because these things are multiplied. There are squares in there and so on. I don't think I can go beyond 16 bits with this. This is why we have fixed point. It's really difficult. But anyway, there you go. An orbit. And although I've been making it a lot more complicated by going for fixed point, essentially this is all the code that there is. And if you were to write this out in sort of Unity terms, you'd be fewer lines of code because there's probably like three lines of code when you're done. Create the orbit. Now, of course, the next thing after this is to do the n body simulations. That's where you have a large number of bodies like this that are all attracted to each other. That's quite fun. I might well do that one for the next stream. But I've gone wildly over time, 40 minutes, like who cares? I hope you enjoyed that, and I'm taking off. So take care, everybody. And one thing, as you know, I did get I started work last week at Bossa Studios,